Okay, so in this lecture, I want to go over some very basic statistics you might be able to do in basic statistics and data analysis you might be able to do in MATLAB. So this will be very basic. It won't be sort of anything too complex, but it just gives you a feel for some basic things you can do in MATLAB to analyze data. Okay. So to get the most information out of our data, we need more complex data analysis methods. Most of these methods are beyond the scope of this unit. However, when you are ready to incorporate more complex analyses, make sure your method is appropriate and necessary assumptions are correct. So there are many articles written by statisticians that sort of decry the use of statistics by scientists or other people that are users of statistics. Essentially, many of the criticisms are around the lack of understanding of what is actually the figures actually mean, applying methods that and not understanding the assumptions behind them and not checking the assumptions. In some cases, the assumptions actually being invalidated. Okay, so this is one example about p-values and the misuse of p-values in the literature. So one of the takeaway messages from this article in Nature is researchers should be instructed to treat statistics as a science and not just a recipe to follow to get a number out, but to have some sort of deeper understanding of what is happening. Okay, so descriptive statistics. So these are sort of numbers that are used to summarize and describe data. So you're probably familiar with many of these. You have the mean. So if you have some data in, say, a row vector in MATLAB, mean x will give you the mean of those, or you can think of this as the average. This is the sort of the mathematical formula this is defined by. Next, you have the standard. So this is next you have the standard deviation, or it's a measure of variability or sort of spread in the data. So the higher the standard deviation, the more the data points are spread out, and you can STD in MATLAB will give you the standard deviation. So this is deviation from the mean of the ith measurement. And then you have the standard error. So when you're calculating the mean, so let's just say you have a population, and the population is, say, all women in Australia. And for this population, you're interested in the average height, okay? So you could, of course, in theory, go out and measure every single woman in Australia. Let's say every female in Australia, 18 years and over, measure their height, do this, and calculate this. And this would be the population mean. But that's very prohibitive. And so what you might do is you might choose a random subsample and calculate the mean of that. And that will give you a sample mean. Now, the sample mean is probably going to be different than the population mean. Hopefully not by too much. Hopefully it gives you a good indication of the population mean. And if you choose different random subsamples of your population, you're actually going to get a different sample mean. So in some sense, so the population mean is a fixed value. It's the mean of the entire population. But taking the sample mean of a subpopulation, of a random subpopulation, is actually a random variable, right? It's going to change depending on what subpopulation you choose. And so since it's a random variable, we can calculate the standard error, which is essentially the amount of variability in this statistic. And so the standard error for this sample mean is given by this, where S is the standard deviation of the so this is an estimate for the sample mean. This is the standard error. S is the standard deviation of your population. Standard deviation of your sample, and N is the number of elements in your sample, or your sample size. Okay, so sorry if that's a little bit confusing. We'll sort of see some examples in a second, which will make it hopefully clearer. Okay, so let's do this. So it says start a new script, Roman Graves summary stats. So let's do that. New script, Roman Graves summary stats. Okay, so in this, what I want to do is load the file rommat. So I'm going to go load rom.mat. Recreate the histograms below. So first of all, I just want to remember exactly. I want to remember exactly what the data in this file is. So I'm going to okay. So when I load, I've got age at death. So the things I'm interested in is the strontium isotope ratio and the difference in the oxygen. So I'm interested in SR ratio and O ratio. So let's come back into my file. So SR ratio and O ratio. Okay. So I'm developing histograms here. So let's just display some histograms. So I'm going to go hist strontium ratio. So I'm going to create a figure. And this is going to be a subplot. I'm going to do two separate subplots. I'm going to do them side by side in a row. So this is going to be one row, two columns. This is going to be the first. And then in here, I'm going to come in. I want to say how many bins do they use? They look maybe 20 bins. Okay, 20. Okay, and then I'm going to put a title. So X label and Y label. So I'm going to go. Y label is occurrence. X label is 8786 strontium isotope ratio. Okay, so that's my first plot. Then I'm going to come down to my second plot and go subplot 1, 2, second plot. And then I'm going to do the same thing, but now for the oxygen ratio. So I'm going to say plot histograms. Okay, so I'm going to copy that into there, and then I'm going to change my X label to delta 18 oxygen. Delta 18 oxygen. Okay. So I'm going to run this just to make sure I haven't made an error in here. Okay, so I've made an error, so let's go and see why it's not working. Oh, so I've misspelled this. So subplot. Okay, let's try it again. Okay, so I have this subplot now. So it doesn't seem to be giving me exactly the number of bins I want. Okay. Oh, that's right, because remember O contains some blank data which are represented by zeros. Okay, so if I look at O ratio, it's got some zeros in here which represent blank data. And I don't think SR ratio does. So if I go SR ratio equals 0, I'm going to try to find something in here that's equal to 0. I won't get anything. Okay. So the first thing I want to do is I want to just get the values that are not equal to 0. So what I want to do is go O ratio not equal to 0. Okay, that's going to give me all the, so you can create a logical vector, and it's going to create a logical vector of the same size of O ratio of just true and falses, or logical values, where 1 is when the value is not equal to 0 and 0 otherwise. When I pass such a logical vector into O ratio, it's just going to pull out all the things for which this is true for. So it's just going to give me all my non-zero values. So let's give this another try. Okay, that's looking better. Okay. Okay. So it says, so we want the mean and the standard deviation. Okay. So let's just divide this up. So at the top, I'm just going to create a new figure for my script. And then I'm going to go strong TM analysis. Okay. Then I'm going to go oxygen analysis. And then in here, I'm going to go plot histograms. Plot histogram. And then here I'm going to go plot histogram. Okay. Display sample statistics. Okay, so I'm going to have the mean is going to be the mean of SR ratio. The standard deviation is going to be the standard deviation of SR ratio. Okay, so I'm going to print fprintf. I'm going to print this. Summary statistics. Okay, then I'm going to fprintf. Oh, fprintf. I'm going to tab in and go mean. Tab again and put the value in, which is going to be Control F. And then I'm going to go new line. And then I'm going to go M for the mean. And then I'm going to do the same thing. I'm going to create an extra new line, so it's a blank space before I do the analysis for the oxygen. So I'm going to go standard deviation. I just want to see what this does, make sure I haven't made an error. So it creates the plot, and okay, I have this. So maybe if I tab it again, that will align it, because mean is shorter, and I don't want to go, and maybe I go a new line here so it spreads it out a little bit more. Okay, maybe I don't want to tab all the way in, just 2 spaces just to make it a little bit neater. Okay, so 87, 86, 210 isotope ratio summary statistic. I've got the mean and I've got the standard deviation. Okay, okay, so it's interesting that the mean and the standard deviation are equal. No, it's not. I've just made a mistake here. Let's run it again. Okay. Okay, so let's do a similar thing for the oxygen. Okay, so remember, I'm only going to do the values that are not equal to 0. These 0 values are blank values. Okay, and I'm going to summary statistics, mean, standard deviation. Okay. So I don't need the extra new line because it's going to be no more data after that. So let me run this. Okay, so this is doing my analysis, which looks good. Let's bring up this figure, the latest figure. Okay, so remember when I'm using figure, it's going to create a new figure each time I run the script. Maybe that's undesirable. And so what I can do is at the beginning of my script, I can call CLF, which stands for clear figures, which clears all currently figures open. So I'm only going to clear all figures, create a new figure, then do my stuff in this figure. Okay. So if I open it, so I've got I've got two figures in here actually. Okay, so it's not working for me. So maybe I misremember the command. So let's have a look. Let's search for CLF. Clear current figure window. Okay. So maybe instead of creating a new figure, I just clear the current figure window. And that's going to be not give me all these figures. Okay. So let's save it. Let's try this again. Okay. So if I run it again, it won't create a new figure, but I will overwrite the current figure window. Okay, so I have this here. Great. So let's have a look at my figure. So we see that the mean of this one's about 0.709, 0.7, so about 0.71. Okay, that looks reasonable. You have some high outliers here perhaps. Then for the data oxygen, looks like the mean's about 26.4. So that looks about reasonable. And there's very little spread in this data. And you can see it sort of sharply peaked, sort of gathered around the mean, whereas there's much more spread in this data, but still not much, right? The range is from say around 24 up to 30. Okay. So parameters. So when comparing different data sets, it is often more useful to present the relative standard deviation and standard error. These parameters are presented as percentages and are equal to the stated parameter divided by the mean times by 100. Okay, so this is essentially the percentage. Relative standard deviation is essentially like a percentage value. Times it by 100, and it's the ratio between the mean and the standard deviation and the mean, and for the same standard error. Okay, so let's come back into our script. Okay, so you see that I'm going to be doing. Okay, so actually, let's come up here and calculate the standard error. So I'm going to go SE is equal to, remember, it's the standard deviation divided by square root, the size of the sample, which is the length SR ratio. Okay. And then I'm going to display the standard error here. Okay, and I'm going to copy this down to here. So it's going to be the number of the ones that are not equal to 0, because that's the blank data. Okay, so I don't want to have the extra line on this one now, because I have the extra new line on this following one. Okay, this is the end, so I don't want the extra new line. Okay, so I'm doing the standard error as well now. Okay, so you see the standard error is in here as well. So this is sort of like the, I guess you can think of this as a sort of like the uncertainty in the mean. So remember, this is a sample mean. This is sort of like our uncertainty in this sample mean, as far as predicting the population mean. Okay. Okay, so the next thing we want to do is these relatives. I want to go at RSD and RSA, relative standard deviation, F print F. I probably need 2 tabs here to go across and align everything because RSC is quite short, and RSD. Okay, so I don't need the double new line only at the end. Do I need that? Okay, so relative standard deviation is 100 times the standard deviation divided by the mean. Okay, and exactly the same formula for this next one, but with the standard error replacing the standard deviation. Okay, so I'm going to have put these two down here for the oxygen analysis. Okay, so now, let's just clear the command window just so it's all clean. Okay, so I'm putting all my summary statistics. Okay. So I've already added the RSD and RSA to our scripts. Okay. Summary statistics that are often useful, for example, the mean, standard deviation, standard error, the relative standard error and the relative standard, the relative standard deviation and the relative standard error, and 95% confidence intervals for the estimate of the mean. So I haven't mentioned what these are, so we will mention these soon. These are these last bit, the 95% confidence intervals. You might remember these if you've done SCI210 or other statistics units. Okay. Remember, the standard deviation of a distribution will not change as n increases, right? I mean, the underlying distribution has a given spread. Okay, it's not going to change. Of course, when you're measuring the standard deviation on your sample, it may change differently because you're not choosing the whole sample, but that's slightly different, right? It's not that. So as n increases, your standard deviation measurement will sort of converge in some sense to the population standard deviation. But if you think about down the line distribution, depending on the as n increases, the standard deviation does not change. However, the standard error should decrease because when we have a larger sample size, our uncertainty in, say, the mean is going to decrease. So you're getting more data. So we become more confident in our ability to estimate the mean and standard deviation as n increases. So the mean and standard deviation is inherent to the underlying distribution and does not change on the sample size. However, we become more confident in our ability to estimate these as our sample size increase. Okay, so now we're going to look at confidence intervals. Okay. So we're going to be looking at this data again. From a few lectures ago when we're looking at Roman burial sites and looking at isotope analysis to indicate whether the person buried was, say, an immigrant or local to Rome. Okay. So confidence intervals. So we begin with alpha to be a significance level, okay? And then the 1 minus alpha confidence interval, which is an interval of values. So this is the lower bound, this is the upper bound for x. It's an interval such that if you repeat a measurement many times, the confidence interval will contain the population mean. This is confidence intervals for the mean, 1 minus alpha % of the time. And this is how you would calculate it. We need the 1 minus alpha, So this is a little bit of a mouthful, so it'll become more obvious when we do some examples. So the way you do this is using students' t-distribution. And I'm not going to explain why you use students' t-distribution. If you're interested, you can go back to your SCI210 textbook or another statistics textbook. Wikipedia's got a nice explanation of this. But for example, this confidence interval on the mean is the sample mean. This is the standard error for the sample mean, and this value here is the 1 minus alpha onto percentile of the student's d-distribution with n minus 1 degrees of freedom, where n is our sample size. Okay, so a common value for alpha is 5%, so a common value for 1 minus alpha is 95%, so people often look at the 95% confidence interval. Other particularly popular values for this would be the 99th percent confidence interval and the 90th percent, and the 90% confidence interval. So the only thing that changes here is this t-value in here when you're calculating these different confidence intervals. Okay, so it's the way we calculate our confidence intervals is that, say we're interested in the 95% confidence level, so this is our confidence level, and we're interested in the confidence interval of the population mean. So we have our sample mean plus or minus our t-value times the standard error associated to the sample mean. This t-value is based on the sample size and the desired confidence level. So we have sample size in this case is 111. So our degrees of freedom is one less than this, 110. The 1 minus an alpha, so the confidence level is 95%. That means the significance level is 5%. We half the significance level, and we subtract this from 1. So we're interested in this percentile of the t-distribution with this degrees of freedom. And I can come to MATLAB to calculate this. You can come over here and go t inverse 1 minus 0.025, 110. It's going to give me my t-value, which is close to 2. Okay, I put this in here and I can calculate my confidence interval. Okay, so let's calculate the confidence intervals for the mean for the this isotope analysis we're doing for the strontium and for the oxygen. Okay, so I'm going to come in here and I'm going to create confidence interval. So first of all, I got my mean, I got my standard error. I'm going to need my t, which is t inverse 1. I'm going to do the 95%, so I'm minus 1.025. And then what's this? How much data do I have? So I'm going to go length of SR ratio. That's my sample size, and I have to subtract 1 to get the degrees of freedom. It's my t-value. Okay. Then I go f print f. Oh, f. Actually, I'm going to do it up here after this one. F print f. 95% CI for the mean. Do a single tab. F new line, and then what am I going to do? It's actually going to be two numbers here, of course, because it's an interval. So I'm going to write it like that, and then my top number is the mean minus t times the standard error, and then my other number is m plus t times the standard error. Okay, I'm going to do exactly the same thing down here. So I'm going to go so this is length of this after we've excluded all the values that are blank. So it's my t-value, and then I'm going to come down here and just copy and paste this line after my mean. Okay, so I'm going to run this now and see what happens. Okay, so it does my plot. Okay, so it doesn't look like it's so I've made an error here. I actually want percent here, not I'm not filling in anything here. So of course when I start with a percentage sign in fprintf, it thinks this is a placeholder for some font, but I actually want a percent sign, so I do a double percent. I'm going to run it. Then I'm going to come back to my window. I'm going to have an estimate for the 95% confidence interval of the mean. Okay, so looking at this, it looks like we have a pretty narrow window. So narrow window. Okay. I didn't change it here. If I come to here, double percent. Run it again. So I come back here, and again, it's still a pretty narrow range of values. Okay. Okay, so what are the benefits of increasing sample size, right? Remember, the standard error is the standard deviation divided by square root of n. So as n increases, the standard error is going to decrease, and so you can think about the confidence interval is measuring, the width of the confidence interval is measuring our uncertainty. So the wider it is, the more uncertain we are. So as this gets smaller, we become more certain of the value. And also, if you look at a table so this is the degrees of freedom, say, as that becomes bigger, you see a drop down in the value. Of course, it doesn't decrease down to 0 like the standard error will as n goes to infinity, but it still decreases down. Okay, so both of these things are going to decrease, and that's going to have the effect of making our uncertainty smaller, making our estimate for the mean more precise. Okay. So, let's have a look at different sample size. Let's start off with a sample size of 2 and go up to 10. So I'm going to create a little graph here in MATLAB. So I'm going to go sample size is 2 through to 10. So, and I've got my t-value, which remember is t inverse. This is for the 95%, so that's 0.025. At these sample sizes, but remember degrees of freedom sample size minus 1. Then I plot the sample size with my t-values. Let's plot it as black circles. Okay, and of course I can go X label sample size, Y label t-value. Come back to my graph. Okay, let's maybe set the axis to be 0 through to 11, 0 through to 14. So my data is a little bit clearer. Maybe I did that wrong. Let's search for axes. Okay. Okay, I thought I did that correctly. Let's try it again. Let me plot this, set my axes, look at my plot. Okay, that's looking better. Then I can put my labels on. I'm not exactly sure what happened before. Okay, so if I have a look at this, I've got my X label, I've got my Y label, sample size, and as you see, T decreases as the sample size increases. Okay. So it is clear that T decreases rapidly until the sample size is greater than about, say, 5, and it starts decreasing much more slowly. Thus, we expect any increase in sample size up to n will help any increase in the sample size up to n equals 5 will help to substantially reduce the size of the confidence interval. Okay. The benefits of so we're going to now do an analysis to study the benefits of increasing sample size. So I'm going to create a new script called sample size, which loads the rome.mat data. So I'm going to come in here and go new file, script, sample size.m. It loads rome.mat. Okay. And then what do? Is I go from the length of 2 to the length of SR ratio for n equals 2 length of SR ratio. Okay. I randomize the order of SR ratio, take a subset of the reordered data, specifically create a new vector equal, because essentially what I'm doing, so what I'm going to be doing here is just taking a random, so n is my sample size. I'm going to be taking, so when n is equal to 2, I'm going to be taking a random subsample of 2 elements from this. And when n is equal to 3, I'm going to take a random 3 element subsample of this, etc. Let's create a pool of elements I can choose from. It's SR ratio. Okay, and then I want to choose create sample. So NaN is going to be 1 row and n elements, and then I'm going to go through each of these elements and fill it in. So I'm going to go for I equals 1 through to n, and okay, so I'm going to get my first element. I'm just going to choose a random element. The way I'm going to do that is choose a random integer from 1 up to the length of the pool of numbers I'm using. Okay. Okay, then I'm going to use that to index in the pool. Actually, I'm going to get call this index j. Okay, and then pool at j is going to be my sample number at I. And then what I'm going to do is I'm going to remove this number from my pool because I've already used it. So I can do this via that. That's going to remove that index number from my pool of numbers to choose from. So I'm not going to be choosing with replacement. Okay, if I choose a number in this particular round, I'm not going to be able to choose it again. So it's going to create my sample. Okay. So I'm going to put a comment, get a random sample sub sample of SR ratio of size n without replacement. Okay. Okay, so this is this. Okay, so the next thing I'm going to do is calculate. So what does it want me to do? So it wants me to save the 95% confidence interval. So the width of the confidence interval. So the width of the confidence interval is 2 times the t value times by the standard error. Okay. So I'm just going to write that there. width, I'm going to call it. Okay, so I need my t-value, which is, I'm going to do, am I doing 95%? Yes. So this is t inverse 0.975, because remember we half the significance level when we subtract it by 1, from 1. Sample size minus 1 for the degrees of freedom. Compute the width of the confidence interval. Okay. My standard error calculation is standard deviation of the data, so my sample, divided by square root the number of sample size, so square root n. Okay, so now I've got the width. Okay, so what I'm going to do now is I'm going to save it. I'm going to save, I'm going to create, so I'm going to want to do this many times to get sort of a good idea of how it changes for different random samples. So I'm going to create a variable called num runs and say let's do 10 runs for each one. Okay, and I go for k is equal to, I just go run is equal to 1 through the num runs, and okay, and then I'm going to store this data into a row vector where, sorry, into an array where the first row corresponds to the sample size and the second row corresponds to the corresponding width calculated with that random subsample of that size. So I'm going to have 2 rows, and how many columns I'm going to have? Well, I'm doing length SR ratio minus 1. This is the different samples I'm doing, and I'm doing each one of these num runs. I'm going to be generating this many data points. Okay, and then I'm going to go populate the data array. Again, I'm just going to create an index of where I'm up to in the data array. So I'm going to go data index starts off at 1. And then for each one, I'm going to go data. So this is both my rows, but so each column corresponds to a particular sort of experiment in terms of getting a random subsample and calculating the width of the confidence in 95% confidence interval of that mean. So I'm going to go data index. Okay, so this is going to be 1 column but 2 rows. So the first row is going to be the sample size, the second row is going to be the width. Okay, and then I'm going to create increase this by 1, so that the next time I hit this, I'm going to be at the next index. Okay, plot data. Plot. So my x value, my sample size is going to be in the first row, but all the columns, and then my width of the confidence interval is going to be my second row, but because that's how I created it. Okay, I'm going to go black dots. I'm going to go x label, sample size, y label, width of 95% confidence interval of mean. I'm going to run this and see what happens. Okay. So if I run it for, if each time I go 100 runs, okay, I get this plot, which shows that, of course, if I'm going up to more and more samples, I have very, very small uncertainty, right? But with small sample sizes, I can have quite a large bit of uncertainty. So sort of imagine the worst case scenario in terms of these samples. You can see it decreases very fast, and then after a while, it sort of decreases much less faster. So the initial increase in the sample size gives us much more confidence than, say, later increases of sample size. So you have these diminishing returns. Okay, so I mean, they plotted it in a different way. Then so the plot looks different because they have a different number of runs for each sample size. But let's have a look. So that's so they've changed the scale to go to so they've changed this X scale, so that's why it looks a little bit different. So we're getting actual data points all the way up here sometimes. Okay. So for a very small data point, we can have a huge increase in the width of the confidence interval, huge uncertainty in the mean. Okay. Okay. So why do we do this? One of the reasons why is so we can compare means. Why we will use interval estimation. So the trend in modern statistics is to move away from hypothesis testing, say using p-values, and concentrate on other approaches, including confidence intervals. Some advantage of confidence intervals: we can estimate the magnitude of any effect. Two flaws with hypothesis testing, including the use of p-values, are we're usually interested in the size of an effect, not simply whether or not an effect exists. Thus, confidence intervals for the effect size are often more appropriate than our hypothesis test. Often the null hypothesis is patently false. For example, when testing means we usually expect small differences, we care more about whether or not the difference is large. Okay, so if we have two populations and we want to see, maybe we have two different populations and we want to see whether the means are different or the same. So this is difference of means. Okay, so if we can assume the two populations have the same standard deviation, which is an assumption, of course, we can pull the standard deviations into this S pooled. Okay, so S pooled is simply essentially combine the two standard deviations using this formula of the two different samples. Then the difference between the means of the two sets of measurements A and B is then estimated from this. This is the 95% confidence level. The degrees of freedom, this is t-value, degrees of freedom is NA, should be NA plus NB minus 2, not NA minus NB, so it's a type of NA plus NB minus 2. Okay, difference between the two sample means. Okay, so for example, if the confidence interval say doesn't contain 0, then we can say at the significance level of 5%, the means are not the same if this confidence interval does not contain 0. Okay. Comparison of experimental results with a known or reference value, for example, comparing measurements to a certified reference sample with the known value. So you have one sample, you want to compare it to a reference value, or you have two sets of unpaired measurements. For example, you have, say, all the students at UNE, you get the men and the women, and you got two different populations, and you measure the different heights. These are unpaired measurements because each of the measurement of the woman is not paired to a measurement of a man. But you have paired data, for example, comparing the improvement between a student's midterm and final exam. So you have one sample which is the midterm, one sample which is the final exam. And then, but the data in the midterm is paired to the data in the exam because the same student's doing it. So that student has two sets of data in it, and it's paired. Okay. Here's the second example: measuring lead in soil. Okay, so you have these two different methods of measuring lead in soil, and so I mean it takes a while to measure it, and so these could be the different measurements between it. Of course, there's going to be errors in the measurements. Okay, and this is the measurement of milligrams of lead per kilogram of soil. Okay, so we're going to write a new script called soil analysis, and it includes the following features. Soil analysis. Okay, so includes the following features. We enter the AAS and ISE data into the script. Okay, so I'm just gonna copy and paste this. Okay, oh, it doesn't do what I want. Okay, so it's done this one, then this one, then this one, then this one. Okay, so AAS, ISE. Okay, so if I delete every second value here, so give me that's the AAS data, and another one is ISE. There's AAS is equal to, what's happening? Okay, this is ISE data. Okay, so we take every second one. Yeah, it looks all right. Okay. Looks like maybe I'm missing something. Okay, so 256, 253, 255, 254, 256, 253. Okay, this is 253 missing. I got 255, 255, 254, 256, 253, 257. Okay, that's looking better. Okay, so I have my AAS data and my ISE data. Okay. Okay. So we've entered this data. So, okay, so I was supposed to put this into a descriptive stats function. I'm not going to bother with that. I'm just going to copy and paste it for now. Okay, so I'm going to Actually, let's do that. Let's create a new function. It's better practice. Okay. Create a script function. Descriptive stats. Sample, and it's not going to return anything. I'm just going to print stuff. Okay, so the mean is sample. The standard I'm not going to print this. I'm going to print this back in my main script. Standard deviation is sample. Sample. This is standard error. I get the t value. Okay, and then I print all of this. Okay, so this is descriptorstats.m. This is where I want it. Okay, that's what I want. Then I'm going to come in here and I'm going to go fprint f stats for AAS. Then I want to go descriptive stats AAS. Then I'm going to do it the same for ISE. Okay, I'm going to just see if this runs properly. And indeed it does, so I get these confidence intervals. Okay. Okay, so this isn't paired data. These are just measurements, and these are just measurements. And then, so these are two different data. We would be interested whether they have the same mean. Okay, write a new function diff mean should calculate the difference of the two samples with 95% confidence. The input should be the two vectors of there. The output should be the mean difference with 95% confidence intervals. Okay. So I'm going to create so this is what called diff means. I'm going to create a new function called diff means.m. Okay, my diff means function is going to have two inputs, sample 1 and sample 2. Confidence interval, this is the left value, this is the right value. I'm just going to call it AB. Okay, I'm going to assume that the standard deviations are the same, are roughly the same, so I can pool them. Let's have a look at this. If I look at standard deviation, they look quite different. Okay, so this may not be a good assumption to pool them. But just for the sake of this example, let's say that the means are the same and that we can pool them. Just for the sake of the example, so let's do that. Okay, so I calculate the means, M1 is mean of sample 1, M2 is mean of sample 2. Do the same for the standard deviations. Okay, then I pool them as pooled. 1, 2, 1, 2, 1, 2. Yep. Okay, so n minus 1, this one squared, n minus 2, this one squared divided by, okay. So I go, just do the sample sizes first. N1 is equal to the length of sample 1, N2 is equal to the length of sample 2. Okay, so I'm going to go N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared square root this. But that all should be over n1 plus n2 to minus 2. Okay, so n1 minus 1 times s1 squared plus n2 minus 1 s2 squared all over n1 plus n2 minus 2 square root of that. Okay, so that's my pooled standard deviation. Next thing I'm interested in is my t-value. So that's t inverse. I'm interested in the 95% confidence level. I go n1 plus n2 to minus 2. That's going to be my there's an error here. It should be plus nb minus 2. Okay, so the mean difference is m1 minus m2. Okay, and so I'm going to go A is equal mean difference minus t-value times s pooled divided by square root n1 plus n2. Okay. And then the b is going to be plus. Okay, so that's going to be this diff means function. Okay. I'm just going to go new line here. 95% confidence interval for difference of means. CI for difference of means is Control F, new line, AB, where my AB comes from my diff means function where I pass in my first sample and my second sample. Okay, I've got an error. Let's see what my error is. Okay, I've made a mistake. I forgot to relabel B. A equals the minus, B equals the plus. Okay. Okay, so this analysis, of course, assumes that there's two standard deviations of the two samples are the same. Of course, they're probably not. They don't look that similar. But even if we assume they were, the difference of the means, so 95% confidence intervals does not include 0 or even close to it. So we could be quite confident in saying that these two means are different, at least at the 5% significance level. Of course, this is assuming the standard deviations are the same, so if they're not, we'd have to modify our analysis. But I don't want to go into extreme depth in this. This just gives you sort of a taste of what you can do with this stuff in MATLAB. Okay, linear regression. So in many cases, you have some data, right? And you might have some sort of thinking, it might be some trend in the data. And you might be able to add this trend line. So modeling the data using linear regression will allow us to find which variables may have an important effect on the outcome measure and estimate the sizes of these effects. So for example, you might say have some output variable, like say weight gain, and you might have some input variables which might be associated to diet, to physical activity, and to regular sleep. And then by looking at maybe instead of the output being weight, it's BMI. And by doing a linear regression on this, or some sort of regression, you can try to find out which factor is the most important factor in terms of having, say, a healthy BMI. That's a sort of simplistic situation, but it sort of gives you an idea of what I mean when I say this. So our models will include one outcome, which is also called a response or a dependent variable, y, and one or more predictor, also called explanatory or independent variables, x1 through to xn. So So of course there's this curve fitting toolbox which you should have access to on Turing, and also with the student licenses that UNE has. MATLAB has several curve fitting functions. Your textbook suggests using polyfit. The function polyfit fits a polynomial of the degree d to specify data points represented by x and y. So d equals 1 would be linear fit. The function returns a polynomial row vector of the coefficients. For a linear fit, d should be equal to 1. Okay. So simple curves are polynomials of different degrees or orders. The degree is the value of the largest exponent. So for example, linear, x, exponent 1 is degree 1. Quadratic, you've got an x squared, so it's degree 2. Cubic is degree 3 because I've got an x cubed. So in MATLAB, a polynomial is represented by a row vector of coefficients. For example, a second order polynomial should be represented by a row vector with length 3. This is going to be the first value, second value, and third value inside that row vector. Okay, so let's try this out. We're going to try this out by just simulating some data. So I'm going to go new script. I'm going to go linear regression. Okay, linear reg. And then inside here, okay. So first thing I'm going to do is I'm going to generate my experimental data that I have. So my data is going to, I'm going to have some theoretical model, right? So let's just say I have my x values, which are, say 1 through to 10. My y values are actually this linear function 2 plus 5 times x, say. So this is my theoretical y. But then I've got some actual y value, which is the experimental, which is going to be the theoretical value that we should get plus some experimental noise and whatever else. So theoretical y plus noise, and let's say the noise is randomly distributed. And I have, how many do I want? I want one row, I want the length of x columns, and let's say 0 mean, and say the standard deviation is say 15. Okay. Let's just plot this data and see what it looks like first before moving on. Okay, so of course we shouldn't plot it exactly like that because we don't know so we should just plot it as single points. Okay, so maybe decrease the standard deviation a little bit so it's not so hard to see the okay, so you can sort of see a linear trend in here. Okay, so that's my theoretical thing. Now what I want to do is I want to polyfit it. Okay, plot experimental data. Okay, now go fit line. So I go, this is going to be my coefficients. So I go polyfit x, y, linear, coefficients. I'm just going to display my coefficients here just to see what they are. Of course, because of the noise, I'm not going to get perfect 5 and 2 here, but hopefully I don't get too far away. I get close to 5, but quite a fair way away from 2, but that's okay. I don't want that, I want sample size. No, I want linear regression. Okay, and then I'm going to plot this. So, but I'm going to plot using much more dense, so it looks like a solid line. So I'm going to go, my x values are going to be, I'm going to go lin space 1 through to 10. do 1,000 points, so it's very smooth. And actually, since it's just a straight line, actually all I need is 2 points, because it's going to, MATLAB will just connect these 2 points by this line anyway. Okay, so my YY is going to be coefficients 1, this is going to be the coefficient of x, the slope, plus coefficients 2, which is going to be the constant term. I'm going to plot xx, yy. This is going to be black circles, and then it's going to be a solid red line. Okay, and I'm going to make sure that hold on so I don't overwrite the previous thing. Okay, so this looks like a fairly good linear fit. Okay. Okay, so let's display the results. Okay, print results, fprintf, slope. Okay, fprintf, true slope. True is what? Control F, new line. I'm going to go slope equals 5, intercept is equal to 2, and just replace those. So I could change it later if I wanted to. And I can just go slope in here now. From fit. Okay, so slope from the fit is the first in the coefficients. Okay, and then I'm going to do the same, but for the y-intercept. Okay, let's see how this goes. Okay, so let's throw an extra tab in here. Let's say I only want 2 decimal places. Okay. Okay, so it's not so bad. Of course, every time it's going to give me something different because I'm generating new data. Of course, if I decreased the noise, the size of the noise, I'm going to get better estimates because there's not so much experimental error to deal with, so I'm getting much closer estimates. Also, if I put the I should be clearing the old figure at the beginning, so this clears the current axis, so I'm not drawing on top of everything from before. Next thing I want to show is rank this back up. Okay. Okay, so I'm not so bad. Okay, but I can be a little bit off still because of this size of the noise. But what happens if I have a lot more data? Let's say I have essentially 100 more experimental points. Okay, so I'm going up in steps of 0.01 instead of 1. Okay, so I have many more data points now. Same amount of noise, but many more data points. Okay, again, my estimates are much more accurate. So for the same level of noise, many more data points, it's going to give me much more accurate estimates of this linear regression. Okay, I'm going to finish here. Hopefully I've given you some rough idea of sort of data analysis you can do in MATLAB. And thank you for listening.